to take this.
Okay, lights are working, sound is working, heart rate 140, so time to get started. Okay, so hello everybody, Sebastian Böhm is my name, and today I'm going to present the prototype of my PhD research project. The name is PULCEO. It stands for a platform for universal and lightweight cloud edge orchestration, and with our platform we would like to tackle some issues in the cloud edge continuum. So edge computing is basically placing of computational resources close to end users, like IoT devices and so on. You can see that here on the right side. So we have a heterogeneous architecture in the end, and our goal is to place some applications maybe onto some nodes in order to meet some service level agreements or quality of experiences, for example, 50 milliseconds of application response time. So we have a heterogeneous architecture and we need to meet that goal, and usually this is done with algorithm strategies or policies, so there are quite a few outside. But the problem is there are many solutions for that, right? And very often you just have a simulated evaluation, so there is no real world deployment as shown by Smolka et al. In 2022. So only 19 out of 99 solutions had a small testbed or real-world evaluation. And this is exactly the point where we want to kick in the end. So we would like to achieve a holistic management, so that you have the entire orchestration workflow at hand. So with creation, monitoring, operation, evaluation, and documentation in the end. So you should simply build your topology with nodes and links, as you can see here before. We have monitoring for the nodes, for the applications, for the links maybe between some particular nodes, and we would like to place applications. We would like to evaluate, support for evaluation with data export and large-scale data analytics, and finally we would like to have an easy documentation, right, that can be shared online or with other researchers as well. And this is exactly the point where our platform comes into play, our platform for universal and lightweight cloud edge orchestration. And this is basically the domain model we extracted from 27 peer-reviewed scientific papers about service placement. So the details are not that important really, so it's just about, so we have nodes. Nodes have a set of metadata like location, group, country, and so on, and those nodes are connected via links. If you remember the first slide, we had just this topology, right? Connected via links. The nodes are provided by some providers. This could be on premises or public cloud providers and so on. And nodes have a set of resources like CPU and memory resources, and those resources are also characterized with several metadata like gflops or cores or shares, as example for the CPU. Nodes can host applications consisting of multiple application components, and for all the core entities, I would say, nodes, applications, and links, you can issue metric requests. So the idea is, by default, nothing is measured, nothing is monitored, but by issuing metric requests, you can simply request particular monitoring values from the platform. And this is, in the end, the architecture of the control plane we developed. So again, it's aligned to a scientific meta study about cloud edge orchestration. So Costa and others, they investigated more than 50 cloud edge orchestrators, and we align our architecture to their work. So it's a pretty basic microservice architecture with one API gateway, and the orchestration solution in the end can just interact with the API gateway, with the platform, and there's also real-time streaming possible for monitoring values, for example, via WebSockets. And the control plane, it just interacts with a set of PULCEO node agents. So the node agents are installed on the nodes, which are supposed to host the applications. Again, we are using a RESTful HTTP API for instructions. Monitoring values are just transmitted via MQTT. And the PULCEO node agent, it hosts the applications, for example here via port 80, TCP, and we have some low-level libraries involved like IPAC3 for measuring the bandwidth between the nodes, and we have ping for measuring the ICMP round-trip time between nodes. And everything is hosted with standalone Kubernetes clusters. Okay, now we come to the case study we can perform. So how does it work in reality? So this is basically the use case we would like to realize. So this is just a representational cloud edge architecture consisting of one cloud layer with one representational node in the US, one fog layer with 2 nodes, and one second fog layer also with one single node. So we can see pretty often in the literature architectures like that. And our goal is to host, to place an application graph as shown here just onto the topology. And the nodes, as you can see here, they have some capabilities. So the first number refers to the number of available CPU cores, second number is memory, and third number is just the storage. And between the nodes you have links, and the first number indicates the ICMP round-trip time, and the second number is the TCP, respectively available UDP bandwidth. So let's get started. It's pretty simple. If you remember the domain model we had, everything is backed up with providers. We have on-premises and cloud providers, and first of all we would like, with the more easier one, the cloud provider. So we offer direct cloud provider integration. So the only thing you need to do is to create a service provider to let the platform get access to the cloud provider. You get some credentials, for example, if you create a Microsoft Azure service principal, and then you just put in the credentials of the service account in the platform. And then you're good to go, and in the second step, you can simply bootstrap the node. So like here, we are just doing one single HTTP, RESTful HTTP request. We just state the previously created provider name, the name of our node, the number of CPU cores we would like to have, the memory, and in the end, the region where the platform should place the node. And that's it. Everything is automatically bootstrapped, and after 30 until 45 seconds, the node is available. For the second node, here the fog node 3 is located in our local data center at university. It's an on-premises node, so in the end, just a virtual machine. You can simply bootstrap the node via the installation script, which is available on GitHub, and then you are just registering the node again via HTTP request to add it to the platform. And you need to state eventually more metadata here because they cannot automatically determine. This is only possible for the cloud provided deployment. And then we can finalize the first subgraph of our topology with a link between fog node 3 and fog node 1. This link is later used for getting the ICMP latency and the TCP bandwidth, and you just issue another HTTP request, and then with the source node and the required destination node, and then the subgraph is completed. What comes next? Monitoring. So we would like to request some values from the platform in order to perform our orchestration algorithm. So far a lot of metrics are supported, for example for nodes. You can see that here, but also the round-trip time and TCP and UDP bandwidth, and we allow for individual and batch assignments. So for example, you would like to have a specific metric for one single entity, or you just want the same metric for all the entities. So if you think of larger topologies consisting of tens or hundreds of nodes, it might be really convenient to just go for the batch assignments to get just the desired value for all the entities in your topology. So this is an example. You just state the type, the link ID. This is a wildcard operator here, so we would like to have it for all the links, and we set the recurrence. So every hour, please measure the ICMP latency between all the nodes in the topology. So this is just an example. We need to do the same potentially if you're interested in other values as well. Okay, then we come to the workload placement. So just as an example here, we place one single instance of this application onto one particular node. So we take an example application here provided by ourselves. It's called Edge IoT Simulator. It just mimics a typical Edge or IoT device. So it sends temperature readings at regular intervals, and it allows us to perform HTTP requests to other instances of the application placed on other nodes to mimic a microservice application. In the end, and it needs one virtual CPU and 1 GB of memory. And this would be the actual preparation of the service placement request. So first of all, we read the CPU resources. So this is the representation we get. So all the metadata that is automatically obtained by our platform. And then we update the CPU resources. We know we need 1,000 shares. And then we just, via HTTP patch request, we are updating the available resources of that node. Somebody might wonder why we need this manual request here. The point is that different orchestration strategies that are part of our domain model require different values. So some authors are working with cores, some authors are working with threads, some authors also consider the maximal frequency. So we need a broad adjustability of all the properties in order to comply to the orchestration strategies which might be eventually implemented. And this is finally the application placement request. So we just select our node, for node 1, we can state a name, and then we put one single application component on this node by just stating the image, port, the protocol which should be exposed, and some environment variables if required. And then everything is running. And finally, we would like to have some evaluations. So to realize the case study I've shown in the beginning, so overall you need 41 API requests to our platform in order to bootstrap everything, in order to create all the nodes, to build the topology, and to place all the nodes, also including the metric request. So you can see here service, endpoint, and all the methods we applied. And this is, for example, one automatically generated part of the report you get. So every orchestration has an automatically generated report, and the following slides are only showing a short overview of everything which is provided. So CPU utilization at around 5%. So this is just the idle resource utilization without any workload deployed. Memory utilization, of course, depending on the capabilities of the nodes. We have this very constant storage utilization because no data is generated. And finally, you can see the retrieved and transmitted traffic per node. And this is caused by the regular bandwidth measurement, right? Because it causes some traffic, of course, in order to determine the available bandwidth. So here you get a concrete overview, a detailed overview about the links we have created before for both ICMP and TCP and UDP, because for this use case we provide a fully configured monitoring system, and you can also see standard deviations, minimums and maximums, and so on. And you can see everything is pretty stable because we use a stable and high performance network between the cloud providers and also from our data center in the university. Also, some analysis for the application resource utilization is provided by node and application, as you can see here. And what is interesting here, you can see regular peaks over time for the CPU utilization for the system component plus your node agent. This is caused by the regular bandwidth measurement. So if you would like to have less utilization, you just need to apply a different configuration. Maybe once an hour, maybe too often, so just set it up to 2 or 3 times a day, for example. And most importantly, the application response time, because this is very often one of the most essential evaluation metrics for placement algorithms. So this is measured by devices, and we provide an endpoint via MQTT. So devices can just send their user-perceived application response time to the platform, and it's automatically included into the report. And you can see here, I mean, the results are obvious in the end. The longer the distance, the higher is the application response time. of course because it is up to the geographical distance, which might be obvious. Yes, for documentation, we provide JSON export for all entities, so nodes, links, metric requests, providers, and reports for two phases, which can be easily published on GitHub. So we have two published here, one for the idle scenario, where no workload was deployed, and one for the load scenario, where we deployed this application graph that you had. Okay, for related solutions, we know there are quite a few. For example, EU projects like the Codeco framework, Fog Atlas, SolarLight, RT, ENAC, etc. So these are good solutions, first of all. But I think the focus is just different, because they do not focus on enhancing reproducibility and practical realization of this advanced service placement, offloading, distributed scaling papers you have in research. It's rather used for industry-grade, large-scale applications. And the major problem is the scheduling schema is very often pre-implemented, so you need to start to replace it, which is a problem and cumbersome, because you are always fighting against this default Kubernetes scheduler, right? So if you have another scheduler, it might be very complicated. So focus on scientific experiments, and sometimes latency and bandwidth measurement is not fully implemented, so you can only re-implement a very small set of service placement solutions. And this also applies to conceptual and prototypical research efforts like Sophos, Unity, etc. So no holistic cloud edge orchestration is possible, so there is no supported evaluation or documentation, and sometimes there is no open source solution provided, which makes it really, really hard to use it, although the concept is pretty nice and pretty good. And I mean cloud and commercial solutions are out of scope, because they're aiming the same thing, like easily connecting IoT or edge devices once, and then that's it. So there's no dynamic reallocation considered. Okay, so I think it's time to come to the end. So our contributions are, first of all, a fully documented RESTful HTTP API that you can easily use to, well, do this holistic cloud edge orchestration approach. So open API specifications are available on GitHub for all the microservices. We have decoupled and holistic cloud edge orchestration with evaluation and documentation, so everything is taken away from the actual orchestration algorithm. So the idea in the end is you have your algorithm, it can be any programming language, it can be machine learning model, whatever you have, but for all the strategies, once you have the decision, okay, place application X, place it on node Y, for example. So this is completely coupled, and the idea is you can just replace in your simulated solution, just replace the line of code where you simulate to place something, just replace it with the RESTful HTTP call, which should be possible, I think, for almost any programming language which is out there. And what is also quite nice and interesting here, we have a scientific and industrial foundation as well. So the platform architecture is based on a scientific meta-study consisting of 50 solutions. We have the complete feature engineering, which you could see in the beginning in the UML diagram, based on scientific and peer-reviewed service placement publications, so far 27, but we plan to increase the number, of course, also with orchestration strategies which are more up-to-date, of course. And the implementation, so the core architecture is following the OpenFlog reference architecture. So the only limitation we have by now is we only have this representational, in the end it's a self-defined architecture, has been implemented with stable network conditions, but luckily we got another paper accepted on this year's SummerSOC 2024, where we did a full real-world realization of a paper by Brocci and Forti from 2017, where we exactly implemented this theoretically defined and simulated solution with our platform. And if you're interested in further material, source code, container pre-built, container images, open API specifications and documentations, just scan this QR code. So everything is available online on GitHub. Okay, then thank you very much.
Okay, so thank you very much. Thanks to all the speakers. We are at the end of this last session of today. I think there's only one point in the agenda.
One important point is
exactly the user reception at 7 p.m. down at the beach bar.
If you don't know where it is, just leave the conference hall, go through the reception, out the pool, not through the pool, just the way down. It will be open. So you start at 7 because there's still